Good deal. Thank you. All right, compounds are chemically combined elements. Chemically combined elements. And we have molecular compounds and we have ionic compounds. How do you determine the difference between molecular compounds and ionic compounds? Anybody know already? It's charge, but it's something simpler than charge. Say it. Metal, non-metal. First element. You look at the first element. That's the simple thing. That's what you do. You look at the first element in the compound. You look at the name of the first element. You look at the symbol, if it's a symbol given to you. You look at the first element in the compound. If the first element in the compound is a nonmetal, then you know you have a molecular compound. If the first element is a metal or ammonium or hydronium, then you know you have an ionic compound. So an ionic compound will be a metal or NH4 or H3O, and I'm going to make a note here, that's ammonium, and this one is hydronium. A metal or ammonium or hydronium written first. Then you know you have an ionic compound. That's what you look for. It's that simple. So how do you know? How do you know if it's a nonmetal or a metal? What do you have in front of you that tells you? The periodic table. Where are the metals located on the periodic table? To the left side of what? The stair step. So you know where the stair step is. It comes down below boron, between boron and aluminum, and then winds its way down. So if you have anything to the left of the stair step, you have a metal. If you have anything to the right of the stair step, you have a nonmetal. So what kind of compounds do nonmetals make? What kind of compounds do nonmetals make if it's only nonmetals? Molecular. It's molecular compounds. So if you have only nonmetals, so what you could do on your periodic table is you could put, and I think, well, actually, you could put on your periodic table. I don't have the same one you have today, but if you have that periodic table, you could make a note somewhere on your periodic table on the right-hand side. Only nonmetals, molecular compounds. Only nonmetals, molecular compounds. So now I'm going to strictly talk about molecular compounds first. Okay, I'm going to strictly talk about those first. So they are nonmetals only. Always nonmetals only. No charges to balance. No charges to balance. No ions. No ions. Because they share electrons. E negative is electrons. Let me write that word just in case. They share electrons. They use prefixes. And I'll even go down here in this free space and remind you, mono is 1, di 2. Do you know these? Keep going. Tri 3, tetra. Keep going. Penta 5. Hexa. Good job. Keep going. Hepta, 7. Octa, 9. Nona. What, I skipped one. Octa is 8. Sorry. Nona is 9. I thought in my head. Octa is 8. Nona is 9. And deca is 10. Good. So those are the prefixes. So if you see a prefix, this is all in your nomenclature notes too, guys. I'm not giving you new information. I'm giving you the same information you have in your nomenclature notes from lab, and they're on my website as well, the Blackboard site. Okay? So if you have the prefix 3, so if it says trisulfide, how many sulfurs is that? 3. That's what that would mean. Okay? That's exactly what that would mean. So molecular, let's review. Nonmetals only, no charges to balance, no ions, they share electrons, you use prefixes, these are the prefixes, and the last thing I want to note is that the smallest particle is called a molecule. The smallest particle is called a molecule. Smallest particle called a molecule. What do molecular compounds not have in them? Say it, anything. There's 2 things really I could say.
No ions.
They have no ions. What else do molecular compounds not have in them? Okay, what else do they not have in them? Metal. They don't have a metal. So should you ever use metals if it has a prefix? So in other words, if you don't know your symbols and elements, and you don't know that S is sulfur, you think it's sodium, but it says disulfur, what should that automatically tell you? Sulfur is a what? Nonmetal or metal? It's a nonmetal because it says di. Okay? So hopefully this kind of gives you maybe a little snippet of everything you learned in nomenclature, but it's here now. All right, now let's go to ionic. Ionic, as I've already said, will have a metal or ammonium or hydronium written first. We must balance charges. In other words, positive must equal negative. That's what that means when I say balance charges. Positive must equal negative. They contain cations and anions. What is the cation? Positive. An anion is negative. Same thing as saying balanced charges, basically, is the fact that I'm saying they contain cations and anions. Not that it really matters to you all so much right this minute, but going along these same steps here, instead of sharing electrons, they transfer electrons. Their electrons are transferred, literally given and taken. Do we use prefixes with ionic compounds? No, no prefixes. No prefixes. So no prefixes. That's one of when you have a name given to you and you see prefixes, that should be your big clue. Oh, this is ionic. If there are no prefixes, this is ionic. And that should be a big clue for you. And then the last thing is the smallest particle. This one is kind of goofy. The smallest particle of an ionic compound is called a formula unit. And that's something we're going to hear more about later when we get into moles. But right now I'm going to go ahead and tell you just to kind of have that in there. Because it is called a formula unit, the smallest particle. So really when we use the term molecule, we're specifically talking about what kind of elements? When non-metal put together, right? Which is why I go to the top of this page. What is the top of this page about? What's the top of this note page about? Diatomic elements. What are diatomic elements? Diatomic, what's the word we just said? What are they? Are they 2 nonmetals put together? So what are they? Diatomic molecules. They're diatomic molecules. You might think of them as a compound, but they're not really a true compound because they're not with another element. Diatomic molecules are molecules because it's two nonmetals put together. To kind of give you a visual of what a diatomic molecule is, think about this is hydrogen, this is hydrogen. So you've got a hydrogen with one valence electron, and I'm going above where you are at this point. Are you on your phone, bud? I've got a hydrogen that's got one valence electron here. I've got a hydrogen that's got one valence electron here. You put those together, now they have two valence electrons. And they're sharing those two valence electrons perfectly. That's a molecule. Hydrogen likes to live this way. Hydrogen only lives this way unless, Katie, it is with something else. Hydrogen is only like this in nature unless it's like H bonded to O bonded to H, like water. Okay? Hydrogen cannot be H, just floating around here, H. It can't be that. It has to be like this because it's more stable like this. And they're sharing the electrons. But it's called the hydrogen molecule because it's two nonmetals put together, because nonmetals put together are called what? Molecules. Isn't that right? Nonmetals put together. So in essence, what you said was somewhat true, but we don't call it that. It is like a molecular compound. Except it's not a compound because it's two to the same thing, okay? So in order to be a compound, you have to be two different elements, okay? All right, so now then let's keep going down. We already, honestly, most of this you probably have already figured out or you already know from your past potentially, maybe not. Cations are what charge? Positive. So cations are positive. They are on the left side of the table. Why? What are they made from? Metals. Made from metals. So who can make a cation? Only a what? Metal. The exceptions to being a metal are ammonium and hydronium. And that's ammonium with a +1 charge, hydronium with a +1 charge. So those are the two exceptions. And basically, I've already written this up there. So ammonium and hydronium are the exceptions. Anions are what charge? Negative. So anions are negative. And they are on the right side of the table. Or polyatomic ions. And polyatomic ions are nonmetals bonded together with extra electrons. That's what polyatomic ions are. Polyatomic ions are nonmetals bonded together with extra electrons. So I want to draw your attention to the ion sheet. You should have already been introduced to this in lab. I'm not sure. I know in my lab you've been introduced to it. I don't know if the other labs, have you been introduced to the ion sheet in the other labs? No? A couple of you know? Okay. Okay. All right. If you have it, grab it. If you don't have it, then you might want to first grab your, I also have a periodic table out. We labeled charges, didn't we, on periodic table last week? Okay. So hopefully you have this. If not, then probably you'll want to make a few notes. So you should have on your periodic table, you should have labeled +1, +2, yes or no? Did you go +2 for zinc, cadmium, mercury? Did you put +1 on silver? +3 on aluminum? -3, -2, -1? Got those labeled? Okay. All right. Make a note if you don't already have this note. Nonmetals are on the right, and when it becomes an ion, it changes to the ending of "ide." These nonmetals will have the ending "ide." They change their ending to "ide." Nonmetals, when they become ions, change their ending to "ide." Metals keep the same name. Now, these in the middle. And basically, they're in the middle all the way to the stair step. You follow what I did? They're in the middle all the way to the stair step, except the ones I have marked specifically. So these have their true charge, the ones that I've already put a number in. But everybody else in this area is considered to be a transition metal. And the transition metals may have varying or different charges. Use Roman numerals or old name. Use Roman numeral or old name. So let's first make sure everybody's following me on this section, okay? So do you see how hydrogen's +1, lithium +1, sodium +1, potassium +1, rubidium +1, cesium +1, silver +1, and we labeled it right there? Is everybody with me? Does everybody see how you don't need to memorize this column right here? Why not? Because it's right here, and you labeled silver. So you don't have to worry about looking at this sheet for this column, because you have it on your periodic table as long as you know how to label your periodic table. The second column is exactly the same way, because the second column, look right here, beryllium, magnesium, calcium, strontium, barium, come over here, zinc, cadmium. Are they all +2? Yes, so you've just memorized this whole column because you have your periodic table labeled. And aluminum is the only one +3, and you've got it labeled +3. Now, somebody's probably thinking, are you going to give us a labeled periodic table? No, I'm not going to give you a labeled periodic table, but I will give you a periodic table, and that's why you have to study where the labels go, and you can label the periodic table. That's a pretty easy thing to do. So if you've done this enough and you practice enough, you'll have these memorized easily if you do all the nomenclature you need to do. All right, on your -1, it's exactly the same way. So your -1 column is over here. Now, I'm going to come back to hydrogen, hydride, because you see it's in both places. I'll come back to it in a minute, but let's deal with fluoride, chloride, bromide, iodide. Are they the -1s? Yes. So that's your -1 column. Go to the -2. Oxide, sulfide. Already labeled right there, -2. Nitride phosphide, already labeled -3. Okay? So this entire top section you just have memorized by knowing where they are on the periodic table. Okay? So no struggles, hopefully, there. Hydrogen and hydride. Hydrogen has the ability of being a positive one or a negative one depending upon who it is with. If hydrogen is with a nonmetal, it will be a +1. If hydrogen is with a metal, it will be -1. Okay? Hydrogen truly is a nonmetal. It truly is a nonmetal, but it can be positive or -1. Most of the time, you will only see it as +1. That's what you will mainly see it as, is +1. So if you want to make a note somewhere, honestly, it's not one of those things I'm going to worry about too much because I'm not sure you even see it very often at all this way. But if you want to make a note, is it will be -1 when with a metal. That is when it will be a -1, is when it is with a metal. Okay? All right, now I'm going to come back to polyatomic ions, flip the page over. So this is the transition metals, and this is what I was just telling you a few minutes ago. I said this. All transition metal ions except zinc, cadmium, and silver, and if you wanted to add in here aluminum because it's on the line, you could, but it's really not a transition metal. But all transition metals may have different, and they call them oxidation states, which is the same thing as charges. For example, titanium 4 and titanium 2. So here is titanium. Titanium can be a +2 charge, or titanium can be a +4 charge. You don't know which one it is unless you know the name. If the name says it's titanium 4, what's the charge? +4. Now, how do you know it's positive? Don't mess this up. How do you know it's positive? It's a metal. Thank you. It's a metal. That's how you know it's positive. All metals are what? Positive. So nowhere over here on this side of the periodic table is anything going to be negative. So if it's titanium, it's going to be positive. If it says titanium 2, it's +2. If it says titanium 4, it's +4. If it says chromium, wherever chromium is here, if it says chromium 3, what charge is it? +3. If it says iron 2, it's +2. If it says cobalt 2, it's +2. If it says vanadium 5, it's +5. So if you have the Roman numeral given to you, that makes it super easy because it's positive whatever the Roman numeral is. If it is an old name, wake up back there. If it's an old name, you have to know it. So if you see cupric, ferrous, mercuric, the good thing about mercuries is they're always +2. Mercury 1 is Hg2. It's kind of a goofy thing. Mercury 1 is Hg2. Mercury 2 is Hg. So the one that says 2 is really just Hg. The one that says 1 is Hg2. Kind of confusing, I agree. It's kind of confusing. But they both are +2 charge. The key to knowing the trick here, you have to memorize the old names, okay? Why do you have to memorize the old names? You may say, well, they're called old names. We're in 2024. Why do we have to memorize the old names? Well, if you look on a vitamin bottle or a mineral bag, very likely you're going to see this. If you look on a bottle of iron, have anybody ever looked at a bottle of what they call pig iron? It's a little bottle of iron it's usually given to pigs. We give it to the goats too when they're anemic. What's it going to say on there? It's going to say ferrous or ferric. It is not going to say iron 2 or iron 3. So you need to know the old names. You need to know that ferrous is iron. You need to know ferric is iron. Okay? So know those old names. The key to this, and if you don't have this written down on your ion sheet, and if you don't have your ion sheet, then I'd write this on a piece of paper somewhere. The Us's are lower charge than the ick for the transition metals. For the transition metals, the Us is a lower charge than the ick. The Us is a lower charge than the ick. Now, you can't say it's always a 2 lower, it's always a 1 lower, it's always lower though. but the us is lower than the ick. All right, so what is the hard thing to learn? The hard thing to learn are the polyatomic ions. The polyatomic ions are the hardest to learn. And so what I'm going to do right now, take the time, is to give you some hints on these. Because I know that they're the harder ones. And I know that it takes memorization. I probably have said this, and I know I'm just blowing smoke, really, but I'll say it again. Quizlet is not the best way to memorize. Quizlet or flashcards are good after you've learned them to study. The best way to learn these is to write them down. And when I say write them down, I mean nothing else going on around you, nothing else, and literally say them aloud. How many songs do you all know? None? None of you know any songs, right? You all know a lot of songs, probably. A lot of you could sing a lot of songs. How do you know the songs you sing? Repetition. And who's singing them? You hear somebody else sing, and then what do you start doing? Singing. Who are you listening to? You. So the best way to memorize for many people, not everybody, but for many people, the best way to memorize is to talk it. When I tell you sometimes, if you heard me say talk your notes out, I'm not joking. You don't listen to me. You hear me, but a lot of you don't listen to me. You listen to you. You listen to you and you hear you say it, and then it gets in here better. So I strongly encourage you to write it down. And when I say write it down, literally 10 times if it's needed. Hydroxide, OH, -1. Hydroxide, OH, -1. Hydroxide, OH, -1. And do exactly that. Say it. Write it. Read it. And you're using 4 senses. You're hearing it, you're seeing it, you're saying it, you're writing it. So you've got all these things in your own body doing it, and you'll learn them. But the hints, chunk them. Chunk them. Do you see how I've chunked them here? Do you see how the cyanide, cyanate, thiocyanate all have something similar? Nitrate, nitrite, perchlorate all the way down to hypochlorite, hydrogen sulfate, hydrogen sulfite, chromate, dichromate, sulfate, sulfate, arsenite, arsenate, phosphate, phosphite. Here's your trick. I'd have no oxygen. If it has I'd, it has absolutely no oxygen. 8 will always have one more oxygen than the ite that it's associated with. So ite is one less oxygen than the 8 it is associated with. Per means one more oxygen than 8. Hypo is one less oxygen than ite. You could also add hydrogen. Adds a +1 charge, so reduces the negative charge by 1. Let me explain that one, and then I'll quit talking for a minute. Do you see how this is? Let's go to sulfate. Do you see how sulfate is SO4 -2? So if you add hydrogen to it, what would the charge be? HSO4 -1. You see that? It was -2, but if a hydrogen itself has a +1, what's it reduced to? -1. Do you understand what I'm saying there? Sulfate is -2 to start with. You add a hydrogen, the hydrogen added a +1, so the whole charge now is what? -1, okay? Is that making sense? I'm seeing blank stares. Does that make sense? Okay, all right. Notice down here, ammonium and hydronium, those are the only positive ones. questions on any of these? All right, have you got everything that I've written? Got it all? Okay. All right, let's keep going then. So, something that is just, we're just adding to our knowledge of compounds. This is definitely not my lecture on chemical reactions. We're going to get to that later. This is just a little bit of an introduction to chemical reactions, finishing up this section on classification of matter. But a chemical equation or a chemical reaction is when two substances, now notice I said substances, not mixtures, two substances, it could be an element or a compound, it could be two compounds, it could be two elements, react together chemically to produce something else, a new substance. So two substances react to produce another substance. So basically we're looking at reactants on the left, which are going to be substances, two or more substances. Could actually be one if it were a certain type of reaction. So actually, I'm not even going to put that. Let's just change it to substances. Substance or substances, because it could be a type of reaction that's called a decomposition, so you might just have one substance on the left. But its reactants yield products. And when again, I need to put a parentheses around the S because it could be a reactant yielding products. It could be reactants yielding product. And so it could be either or. So reactants producing products. And again, the products are substances. Are we dealing with mixtures here at all? Are we dealing with mixtures at all here? No, we're not dealing with mixtures at all. We're dealing with chemically combined substances. So what I'm wanting out of this little section, all I'm wanting you to be able to do at this point in this class is to read it. I'm not asking you to balance it. That's what you've done. Probably many of you have already balanced equations. How many of you have balanced equations in past classes? Okay, that's most of you have. I'm not asking you to balance it. We will do that later, but that's not what I'm asking you to do right now. Right now, all I'm saying is read it. Read what I've written. Be able to determine what she means. What does this mean? The way I've written it. So let's look at this one. What does this mean? That's what I'm asking, and these are my questions. So first of all, you do have to know that a balanced equation contains the same number of atoms of each element on both sides. Again, you're not having to balance it. I'm giving it to you balanced. This is a balanced equation, okay? I will give you a balanced equation. I will ask you questions about the balanced equation. So one of my questions is, who are the reactants? Who, though? Specifically, who are the reactants? Who is Na? Sodium. Sodium and, not chloride, chlorine. Sodium and chlorine. Why is it not chloride as the reactant? Because it's not in a compound. It's not in a compound. What is it here? It's just an element. Now somebody's asking, but it's got two. Say it. It's not charges. Not charges. Thank you. It's a diatomic element. Guys, I want to remind you, chemistry builds upon itself. Chemistry builds upon itself. I want to tell you something I've learned, and maybe you did not learn this way, but something that I have discovered by being a substitute, I sub Monday, Wednesday, Friday, every Monday, Wednesday, Friday in elementary school. And what I've discovered in substitute teaching, because I homeschooled, what I've discovered is that many of you did not learn things again and again and again. What I call the spiral technique, which is what they call that in education, many of you learned something, you tested over it, and then you didn't revisit it for 2 or 3 years. I'm sorry. I don't like that. And I hate it whenever, because I'll ask, because I'm doing RTI, some of y'all know what that is. I do RTI, and what they're, I'll be like, okay, what are we working on? And I'm like, can I teach them da-da-da? Well, no, they learned that in 2nd grade. We don't do that in 4th grade. What do you mean you're not doing decimals in 4th grade? Don't they need to revisit it? No, we're not tested on it in 4th grade, so we're not doing it. You cannot have that concept or philosophy in chemistry. You have to go back. Look, what did we just talk about? What did we just talk about? Right there, what did we just talk about? Who are those? Diatomic elements. That's why you've got to study every day. Have you read in your syllabus how to pass this class? Might be time to read that. How to pass this class is you study every day, and you have to pay attention to what you've learned in the past. You cannot say, oh, we did that yesterday, it's not important today. Chemistry is great because it builds upon itself every day. Why is chlorine written Cl2 right there? Because chlorine does not exist alone in nature. It must be in diatomic state or combined with other elements in a compound. Now look what happens. Right here. Look what happens. Sodium is the reactant. Chlorine is the reactant. Sodium, though, is written as just Na. Why can sodium be written as just Na? It's not diatomic. Why is chlorine written as Cl2? Because it is diatomic. Is this still an element, and is this still an element? Yes. Now, why is Cl not Cl2? Because it's in a compound with another atom. It can do that. The point is can you ever have Cl? No. You can never have just Cl. So learning how to read this equation, that's what we're talking about here. So now let's go deeper. We know that sodium and chlorine individually are the reactants. Now let's be more specific. How many atoms of sodium are on this reactant side? 2. Why? That 2 in front. So there are 2 atoms of Na reacting with, now what's the proper word for this? One, what? One diatomic molecule of chlorine. And we can leave off the word diatomic because diatomic and molecule basically mean the same thing here. We can say one molecule of Cl2. And then for your sake, you probably want to make a note, Cl2 is diatomic, just to help you when you go back to study this. So 2 atoms of sodium reacting with 1 molecule of chlorine, and the 1 molecule of chlorine contains what? 2 what? 2 atoms of chlorine. Does that make sense? Think about the word diatomic. What does diatomic mean? 2 atoms. So this 1 molecule of chlorine contains 2 atoms of Cl. I'm not trying to make this more difficult. I'm trying to break it down. I feel like I may be making it more difficult. Does that make sense? Diatomic means 2 atom molecules, 2 atomed elements. That's what that means. So really on this left side, do we have 2 atoms of sodium and 2 atoms of chlorine? Or we could say we have 2 atoms of sodium and 1 molecule of chlorine. Do you see how that's the same thing? All right, now, who or what are the products? Sodium chloride. So we can say sodium chloride. Now we're going to break that down in just a minute. So we can say that it's sodium chloride just in general is the product. Sodium chloride is the product. Now let's break that down further. Let's break that down further in words. We can say it's 2. Now, what's the smallest particle of an ionic compound called? I told you, formula unit. So it's 2 formula units of NaCl. Again, that's on the previous page. The smallest particle of an ionic compound is called a formula unit. So it's 2 formula units of sodium chloride, but the 2 formula units of sodium chloride contain what? 2 atoms of what? Sodium and 2 atoms of chlorine. And so if you want to put a note here containing, so the 2 formula units of sodium chloride contain 2 atoms of sodium and 2 atoms of chlorine. All of that, to go back up and read again, a balanced equation contains what? Wake up over there. The same number of atoms of each element on each side. Do we have 2 atoms of sodium on the left? How many do we have on the right? 2 atoms of sodium. Do we have 2 atoms of chlorine on the left? Do we have 2 atoms of chlorine on the right? Are they the same on both sides though? No. Did they chemically combine? Yes. So this is a chemical reaction. All right? Again, you are not going to have to balance right now, but you should be able to read just like I did. Now, what I may also do, and I can't remember if I do or not, I know I've done it in the past, but what I have done in the past is just to give you kind of a, have you really been learning anything in lab? I will give you one, and then I'll say, what's the name of that? Just to see if you know it. Maybe a bonus question. Now, in our case, all of us know this is sodium chloride, but it might be one I haven't done in class, and so just to see, I'm not saying sure you will have one like that, but in all honesty, have you been learning that in lab? Have you been learning simple ionic compounds in lab? Is that going to be on this week's quiz? Was it on this week's quiz? Yesterday, who had lab yesterday? Was it on your quiz? That's right. So in all honesty, if you've been tested on it in lab, you could be tested on it in here on Thursday or next Tuesday, okay? I'm not saying I will, but you should be able to know it. You should know, okay? All right, the last thing I want to mention here, it's kind of thrown in at the end. It's something I probably should have talked about before. Want to just point this out. We use the term mass and weight. Actually, there's two things I'm going to do here, but we use the term mass and weight interchangeably. In lab, for instance, we will say weigh out, and then I might say get the mass. I may say both of those things. Weigh it out, get the mass. Is there a difference? Yes. Who can tell me what the difference is?
Mass is the space that you take up, and weight is the force of the gravitational force.
Mass is not space, that's volume. But you're right on the weight. Tell me about weight again. Weight is the measure of what?
The gravitational force.
That's right. Weight is the measure of the Earth's gravitational attraction for an object. Weight is the measure of the Earth's gravitational attraction for an object. Mass is the amount of matter in an object, and it is constant with regard to location. So let's take this little clock up here, for instance. This clock, this clock has a certain amount of matter in the object, yes? If I were to take the batteries out of the back, would it have the same amount of matter? No, because I've removed some of the matter. But as it is, it has a certain amount of matter. There's a certain amount of matter in this object. If I take this clock to the moon, though, it's still going to have the same amount of matter. What's it going to do, though? The weight is going to change. Will it float? Yes. Why? There you go. There you go. So a quick weight loss plan is what? Go to the moon. But will my pants fit any looser? No. Why? There's still the amount of junk in the trunk, right? There's still the amount of junk in the trunk. That's not going to change. That's not going to change. The amount of junk in the trunks is still going to be there. So the problem is if I want to lose weight, it's just I got to lose what? Mass. If I want to lose weight, I've got to lose mass. But theoretically, if I wanted to go live on the moon, I definitely would have less weight, right? So I'm not overweight. The Earth just loves me. Is that what you're really saying? The Earth just has a strong gravitational attraction for me. Stronger than if you weigh less than me, right? The more you weigh, the more the Earth loves you. Is that correct? Does that kind of make sense? Kind of fun. All right, last thing I need to do. I should have done it up here, and I meant to, and I forgot to. Last thing, I promise, on this section, and then we're going to move on to the next page. But just to make sure we're all in the same understanding here, if I were to give you a compound, formula like that, first thing I want you to do is just looking at your periodic table and your polyatomic ion sheet, let's figure out the name of it. Who's Ba? Barium. Do I use prefixes? Why not? Where is barium located on the periodic table? It's a metal, isn't it? So does it need prefixes? No. Okay. Who is PO4? Phosphate. Very good. Right here it is. PO4 is phosphate. So the name is barium phosphate. No prefixes. It's ionic. No prefixes. It's ionic. Now, let me ask a question. I'm going to go backwards. We're going to just kind of ignore this for a minute, and I'm going to do this for you. I only give you the words. I only give you the name. How do you figure out the formula? Well, when you have the name given to you, put the charge above the name. What's barium's charge? +2. What's phosphate's charge? -3. How do they know that so fast? Because they've been studying or they've had another class where they've learned them. Now, how do you figure out the balancing? What is balancing charges? Balancing charges means your positives have to equal your negatives. The easiest way we teach to do this, obviously a lot of you can just see it, but if you don't see it immediately, then what we say is crisscross the charges. So bring the number down as a subscript over here, bring the number down as a subscript over there, and now what's the subscript for barium? So what's the symbol for barium? So it's Ba what? 3. What's phosphate's symbol? This is why you have to memorize them. PO4. Because it is a polyatomic ion, you must put it in parentheses. And then how many do we need? 2. So notice, both ways. Did we get the same thing? So that's why it's not a prefix. There's no prefixes there.
So the charge just disappears when it comes down?
The charge sign disappears, correct. Because what you're really doing is you're saying 3 times +2 is what? +6. -3 times 2 is -6. Does a +6 equal a -6? Yes. So you need 2 phosphates to balance out 3 bariums. Is that making sense? Now, what does this or this mean? How many atoms of barium are here? 3. So this whole thing is 3 atoms of barium. Now I'm breaking it down into atoms, total only atoms. It's 3 atoms of barium. How many atoms of phosphorus? 2. See how the 2 is outside the parentheses? That means 2 of everything inside the parentheses. So that's 2 phosphoruses. So 2 atoms of P. How many atoms of O? 8. So 8 atoms of O. Total. That's what we're saying here. Total. Total. That's what that means. Does that help a little bit maybe? Okay. What I did here is lab and nomenclature. What I did here is what I'm trying to get you to do for my class just right now is be able to read a formula, read an equation. That's what I'm trying to get you to do, okay? All right, next topic now is matter, the properties. So we've been dealing with the basically the classification of matter. Now we're going to be dealing with the properties of matter. And it goes, I want us to actually start with chemical properties because that's what we've basically just been talking about. Chemical properties and chemical changes both are dealing with what? Chemical, what? Reactions. Chemical properties and chemical changes are dealing with chemical reactions. You cannot have or you cannot talk about a chemical property unless you're discussing what the chemical reaction of that substance is. So if I said to you, a property of water is that it reacts with sodium metal violently, then am I talking about a chemical property or physical property? One word I use there should tell you immediately. What word did I use? React. So what am I talking about? Chemical. If I say react, am I talking about a chemical property? Even if I said it does not react, then am I dealing with a chemical property? Yes. If I say to you, water is a liquid at room temperature, what is that? Physical property. Does that have anything to do with water reacting? If we're talking about a reaction, then it's going to be a chemical property or chemical change. If we're talking nothing about a reaction, now the problem is sometimes we don't know what reactions mean. What if I say it burns? Is that a chemical reaction? Yes, burning is a chemical reaction. Now, let's go backwards. Do you remember all those things, separating mixtures I gave you? All those different ways, and that's what you're spending 2 lab periods. We're spending 2 lab periods dealing with separating mixtures. You deal with it this week, which is chromatography. You're going to deal with it next week, which is elements, compounds, and mixtures, and you're separating mixtures. Wake up over here, buddy. So we're dealing for 2 weeks, we're dealing with separating mixtures. If you can't physically separate it, what must it be? Chemical. If you can't physically fix it back, it must have been chemical. Anytime anything burns, can you physically fix it back? No. Is burning, I don't know if any of you all ever do this or not, but sometimes I'll just have a barn clean out. And all those junky pieces of wood that you've saved and all this junk of cardboard you got and all this junk. You just clean it out and you make a big pile and you burn it. Is that like the most cathartic experience to do that? It's like, dude, man, that's burning is just clean. Kind of. It's really not at all.
That's definitely satisfying.
It is definitely satisfying. It is
Probably not
satisfying.
very sanitary.
But can we get it back?
Unfortunately.
Unfortunately, no. You know, the other day I was like, I burned some pieces of plywood and did not big pieces, but small pieces. I'm like, man, I could have used that up in the attic on the floor, but it's gone. Can I go back and get that back? No, it's gone. So burning, we can't get back. So burning is definitely what? Chemical. Burning is chemical. That's exactly right. So physical properties can be determined without changing the chemical composition. Chemical properties are determined by changing the chemical composition, and they describe the substance's ability to make new substances. I'm going to give you examples, okay? And that's the best thing to do, and then when you're in lab this week and next week, you can start to realize, oh, this is what we're talking about. Chemical physical changes, chemical physical properties. Odor, color, texture, taste. Now I'm going to stop right there. Do we ever taste anything in lab? No. We don't ever taste anything in lab, ever. But let me go back again. Everything I've just described there, other than taste, some of you have such good observation skills. Some of you are so good about observing. Some of you know exactly, if I've worn this shirt before, you know exactly whether I've worn these pants before, you may pay attention to my shoes. I don't have a clue myself. I don't even look at myself in the morning, really. Once I get halfway done, I quit looking. I noticed the cowboy hat. That is what I noticed because it's different, but that's unusual for me. I noticed one day he didn't wear his cowboy hat. Typically, though, I don't notice those things because I'm not a person who observes looking at people very closely. Somebody could just rob me blind and I wouldn't have a clue what they look like. I typically would know what they smell like, though. I have a really good nose, so if you smoke, I'm going to know you smoke. Because that's where I'm. But everything, like when you do that with me, when we see each other, first impressions, when we look, are we noticing physical properties? Now, we don't taste people. But other than that, do we notice odor, color, texture, taste? Some of you are very texture people. Some of you notice, okay, that looks like a really soft t-shirt, or man, that looks really uncomfortable. Because you're texture people. Again, when we do that, are we changing chemically that situation, that person, that substance? No. Now, this one is one, all those make sense because it's what we do. Now, density. You've done density. You've determined density. Is determining density changing the substance chemically? Not at all. Not at all does it change it chemically. Not at all. Why? What are you finding? Mass and volume. Mass and volume. Does it change it chemically to find mass and volume? Did it change that piece of metal when you put it into the water to find the volume? No. Would we have given you something that would have reacted with water if to tell you to put it in water? No. But if it had reacted in water, would we have been talking about physical property or chemical property? Chemical property. Okay? All right, so density and solubility. If something is soluble in something else, like whenever we put sugar in water. And again, this is a great example of what I've already said. Can you take it back out? If we dissolve sugar in water, can you take that sugar back out? How? You're right, correct. What do? You evaporate the water out. Then do you have the sugar left over? Yes. Did that take anything chemical to do that? Strictly physical, which means boiling, melting, freezing, are all of those physical or chemical? I'm not saying burning. I said boiling, freezing, melting. What are they? Physical. So boiling, freezing, melting. So if I ask you the boiling point, the freezing point, the melting point, all of those are what? Chemical or physical properties? Physical properties. That's exactly right. All right, chemical properties. Basically, it's exactly what I've already talked about today. Example would be sodium reacts with water violently to produce hydrogen gas and sodium hydroxide. Am I describing a substance's ability to make new substances? That's a chemical property. That's a chemical property. Or another example would be to say iron rust when exposed to air or water. Can you get that rust back into iron? If you don't believe me on that one, here's an experiment for you to do. Take a magnet and touch something that's iron. Scrape off rust gently. Try not to get any iron pieces, but scrape off rust. Try to get the magnet to pick up the rust. Is it going to? No, it will not pick up the rust. Why? Because rust is iron plus oxygen already chemically combined. It will not, because it's a new substance, and iron oxide is not going to be attracted to a magnet. That's how you know.
I think it's also in rock, isn't it?
It can be, yes. Yes. Okay? All right. Now, physical and chemical changes. Here's again, basically we're describing the same thing. I'm going to give you some examples of physical are going to be any of these changes. So if you simply have a color change, such as painting or coloring on a sheet of paper, that would be a what? Physical. That would be a physical change. But some color changes are going to be chemical. So you have to pay attention to whether you could get it back out. Could you get it back out? Could you change it back to the original scenario? All right, so chemical changes, I'm going to give you some examples of chemical changes. Rusting, digestion, burning, those are all chemical changes. And I'm going to make a note here. Many times, a chemical change also has a physical change, but you call it a chemical change. It's the chemical change that caused the physical change. And I'm going to give you one more example that's probably one of the harder examples people get a little confused about. Boiling an egg. Boiling an egg. Is that a chemical change or a physical change? I want you to think all your senses, with all your senses. Imagine, picture, eat, peel, think, boil that egg. And what is it? Physical or chemical? It's chemical. It's chemical. Now, does it also have a physical change? It changed from a liquid to a solid, but is changing from a liquid to a solid chemical at all? Just in itself? Liquid to solid would be physical. How do we know boiling an egg is chemical? What is one of your senses that tells you boiling an egg is chemical? If I had a boiled egg up here and I started peeling it and I started eating it and I had 2 or 3 of these, what might some of you start to do? Smell it. Does a boiled egg have a different smell than a raw egg? Yes. Does that mean there was a gas produced that's different than what you had? That's the easiest way to think of it. Now I know you think, well, smell in itself, only smell is a physical property. Just what does something smell like is a physical property. But if there is a change in odor, then what is that probably indicative of? A gas formation. And a gas formation would be a chemical change. So let's add that. So boiling an egg is chemical due to gas formation causing smell. I think that'd be the easiest way, but it is chemical. And that's one that is a little confusing for some people. Okay, I'm going to stop right here. This is a good place to stop, and I've got somewhere I can be. So I'm going to stop right here. Guys, bring your calculator Thursdays because we've got a lot more math to do on Thursday. I will see you then, okay?